Tech Talk N. Venkat Sai, roll number 23951802226. Branch and year Electrical and Electronics Engineering, second year. Subject Control Systems. Topic A study of spacecraft reaction thruster configuration for attitude control system. Spacecraft reaction thruster configuration for attitude control. This presentation explores the fundamental principles of spacecraft reaction thruster and develop into different thrusters configuration for attitude control system. We will examine the advantages and disadvantages of various configurations, analyze the performance metrics, and discuss consideration for optimal design and development. Introduction. Attitude control system overview. Importance of attitude control. Attitude control is crucial for spacecraft operations, enabling precise pointing and antennas, solar panels, and scientist instruments. Without it, spacecraft would tumble uncontrollably, hindering data accuracy and mission success. Role and reaction thrusters. Reaction thrusters are kept actuators in attitude control systems. They generate small bursts and thrust to adjust the spacecraft orientation, effectively countering external distributions like gravity gradients and atmospheric drag. Reaction thruster principles. How they work. Propellant explosion. Reaction thrusters expel a propellant, typically a gas like hydrogen, through a nozzle. The momentum of a expelled propellant creates a reaction force, pushing the spacecraft in the opposite directions. Impulse and momentum. The amount of thrust generated is directly proportional to the propellant mass flow rate and the exact velocity. Thrusters' higher exact velocities produce greater impulse, enabling more efficient attitude adjustments. Common thrusters configuration. Single, dual, and quad nozzles. Single nozzle. A single nozzle thruster provides simple and direct control. It is suitable for smaller spacecraft with less complex attitude requirements. Dual nozzles. Dual nozzles offers increased maneuverability by providing thrust in two directions. This configuration is often used to more complex attitude control tasks such as station keeping or maneuvering in orbit. Quad nozzles. Quad nozzles provides the higher level of control by allowing for thrust in four directions. This configuration is commonly used for large spacecraft with strengthened pointing requirement like deep space missions. Performance metrics, thrust, ISP, and duty cycle. Thrust. Thrust is the force generated by the thrusters measured in networks. Higher thrust enables faster attitude changes but consumes more propellant. Specific impulse. Specific impulse is a measure to thruster efficiency, indicating the amount of thrust produced per unit mass of propellant consumed. Higher specific impulse value imply greater efficiency. Duty cycle. Duty cycles refers to the percentage of time the thruster is actively firing. It's crucial to manage the duty cycle provide excessive propellant consumption and minimize wear on thruster components. Thrust. Thrust is the force generated by the thruster, measured in networks, newtons. Higher thrust enables faster attitude changes but consumes more propellant. Specific impulse. Specific impulse is a measure of thruster efficiency indicating the amount of thruster produced per unit mass of propellant consumed. Higher specific impulse value imply greater efficiency. Duty cycle. Duty cycle refers to the percentage of time the thrusters is actively firing. It's crucial to manage the duty cycle to avoid expensive propellant consumption and minimize wear on thruster components. Simulation setup. Modeling spacecraft dynamics. 6 of modeling. Spacecraft dynamics are typically modeled using 6 degree of freedom 6 DOF simulation, which accounts for the spacecraft translation and rotational motion, force and moment balance. The simulation considered all forces acting on the spacecraft, including gravity, atmospheric drag, solar radiation pressure, and thruster forces. It also accounts for the spacecraft's inertia and moment of inertia. Control algorithm implementation. This simulation incorporates the spacecraft attitudes control algorithms which determines the required thrusters firing sequences based on sensor readings and desired attitudes. Result configuration comparison in orbits pointing accuracy. Different configurations can result in varying levels of pointing accuracy, which is the crucial for tasks like communication and scientific observations. Fuel consumption. Fuel consumption is a crucial parameter for mission longevity. Configuration with higher ASP or lower duty cycles can improve propellant efficiency. Maneuver time. Maneuver time refers to the time required for the spacecraft to change its attitude. Configuration with higher thrust can achieve faster maneuvers but consume more fuel. Case study applications to a specific missions. Mission objectives. Consider the mission objectives such as pointing accuracy, maneuver frequency, and mission duration. These factors will influence the choice of thruster configuration. Spacecraft design. The spacecraft size, mass, and inertia play a significant role in determining the appropriate thrusters and their placements on the spacecraft. Environmental conditions. Factors like atmospheric drag, solar radiation, pressure, and gravity gradient can affect the spacecraft attitude by stability and influence thruster selections. Challenges and limitations. Thruster placements and fuel consumption. Thrust vector alignment. Precious thruster placements is crucial for achieving accurate attitude control. Misalignment can lead to unwanted torque and affect pointing stability. Propellant management. Managing propellant consumption is essential for mission longevity. Optimizing thrusters, firing sequence, and minimizing the duty cycle can significantly extend the mission lifetime. Thrusters life. Thrusters have a limited lifespan due to wear and tear from repeated fairings. Selecting configuration that minimize the number of firing can extend the thruster's operation life. Conclusion: choosing the right configuration for your spacecraft. Selecting the optimal reaction thrusters configuration for attitude control is a multifaceted process. It requires careful consideration of the spacecraft mission objectives, design constructions, and environmental factors. This presentation have provided the framework for evaluation different configuration, analyzing performance metrics, and addressing key challenges. By considering these factors, engineer can choose the most suitable thrusters configuration for their spacecraft, ensuring successful attitude control for the mission success. Thank you.